to look at a preparatory examination, Physical Sciences, Paper 2, which is our chemistry, and it's a September paper. Marks is 150, and then the duration is 3 hours. Right, so we're going to proceed to the next page, which is our instructions. Then we're going to dive into our multiple choice questions there, starting with question 1.1, right? So it reads here, which one of the following is a tertiary alcohol, right? So for us to be able to answer this one, we need to start by defining a tertiary alcohol, right? So to define a tertiary alcohol, we're saying we're going to define it as the C atom bonded to the hydroxyl group. Hydroxyl group is bonded to three other C atoms, right? Three other C atoms. Like that, right? So this is the definition of a tertiary alcohol. Then after that, we're going to look at our option A, which is butane, one all there. I'm going to say butane has got 4 carbons, 1, 2, 3, 4, right? So we're told on carbon number 1 there, I will make it this one. Carbon number 1 is bonded to what? To an OH, right? So having said that, now we're going to focus on this C that is actually bonded to this hydroxyl group. We can see it's only bonded to one other carbon. So our option A is incorrect there. So take note, the rest are hydrogens, but I'm not going to indicate them for now. Then second option, which is our option B, says propane 2 also. Prop means 3 carbons. So it's 1, 2, 3 like that, right? Then on carbon number 2, we're told that's where we're having our alcohol, right? So it's going to be NOH there, right? So after that, hydrogens like that. Remember, carbon bonds 4 times. Then our main focus is going to be on this carbon that is actually bonded to the hydroxyl group, right? So it is also bonded to, other carbons 1, 2, right? So it means this one is a secondary alcohol. Therefore, that answer there is incorrect. Then we proceed to option C, which says 2-methyl butane 1-ol, right? So the longest chain is 4. There is going to be 1, 2, 3, 4. And then on carbon number 2, we're told also there is a methyl there, right? So it's going to be a CH3 like that. And then after that, also what we know about this is that now we also have an OH, right? So an OH that is bonded on what? 1-ol. So it means the first carbon there, right? OH there, right? So this is what we're having there. Then after that, we can look at this C atom, right? So we can see it's only bonded to what? To one other carbon. Therefore, option C is also incorrect. Then we proceed to option D, which is methyl propane 2-ol, right? So propane means prop means 3 carbons, 1, 2, and 3. Then also we now know that we are having a propane 2-ol, the alcohol or the hydroxyl group is bonded on carbon number 2. Then after that, we also have the methyl group, which is our CH3 there, right? So having said that, now we can see that if we were to focus on our C that is bonded to this OH there, is also bonded to other carbons 1, 2, 3. So our correct answer there is going to be option D, which is our methyl propane 2-ol. So D is the correct answer there. Then we proceed to question number 2, which reads there, which consider the following organic compounds. We're considering the organic compounds there. Then we're having option 1, 2, 3 until 4. And then which one of the above are chain isomers, right? So we're looking for what we refer to as what chain isomers. Same molecular formula, but different what chains there, right? So therefore, now let's look at the first option there. Given there, I can see the first one there is actually going to be how many there are. According to this, I'm going to have the name that says 2-methyl, 2.3, 2.3, dimethyl, butane, right? Butane, like that, okay? So 2-methyl, 2.3 dimethyl butane. So allow me to write on this side. So we're having 2.3 dimethyl butane, right? So this is the structure that we're having there. So for 2.3 dimethyl, we're going to say have something like this: 1, 2, 3, 4 carbons there. Then after that, now we know on this here we're having our methyl groups, right? So I'm going to say an H and H there, an H there. Again here on this one there, I'm also going to have another CH3, right? An H, an H, an H like that, right? Then the rest they are actually going to be our hydrogens like that, right? So this is our option A there, or is item 1 there. Okay, so this is our methyl butane, right? Then we look at option 2 there, which is this one there. According to that, is our 2-methyl pentane, right? So option 2 is 2-methyl 2 dash methyl pentane, right? Okay, pentane, like that. Okay, so 2-methyl pentane. But from the look of things here, if I can see here, this was supposed to be a CH3. Generally, because it's a CH2, it means this one I can actually render this one out automatically. Then let me focus on option number 3. So option number 3 is actually going to give me a value of what? 3 IUPAC name, 3-methyl pentane, 3 dash methyl pentane. So 3-methyl pentane, right? Okay, this is what I'm actually having there, right? From the look of things here, I think these two, they've already have the same molecular formula, which is C6 at the top there, then H what 14. And then for option 3 also, I'm having there a C6 then H14 there, right? So having said that, now if we're to look at option 4 there, it seems like because we're having this there, it's actually going to have what? A triple bond, which is more of what? An alkyne. And then from the molecular formula, I can say 6 H 10 there, therefore is actually incorrect. So the correct options that I'm having there are going to be option 1 and 3. So it means now the correct answer there that I'm actually going to have there for number 2 is D there. This is 1 and 3, right? They've got the same molecular formula, but different what change there. Then we proceed to question 1.3, which reads, which homologous series is a formyl group, the functional group of, right? So now we're looking for the formyl group, which is the functional group of what, right? So start with the carboxylic acid, right? The name for carboxylic acid there in terms of the group is referred to as the carboxyl group, right? So carboxyl group, automatically you can see this is the wrong options. Then for ketone, we have our carbonyl group there, and then carbonyl group there. Then for option D, C, the what we are having there is our formyl group, right? So this is our formyl group, right? So according to this, we're looking for the one that has got a formyl group. So our option C is the correct answer. Therefore, our correct answer there is going to be option C. Then we proceed to question 1.4. So question 1.4 there reads, a piece of magnesium ribbon reacts with excess hydrochloric acid according to the following equation. Then this is the equation that is actually given. Then after that, we are asked which one of the following changes will not affect the reaction rate, right? So something that will actually not speed up or slow down the reaction rate there, right? The one that does not have any impact, right? So we're having the option A that says putting the reaction mixture in hot water. Therefore, in terms of this, we're talking about what temperature as a factor. So we do know the temperature. If there's a change in temperature, the rate of reaction also what changes there, right? So remember, temperature is the average kinetic energy within the particles there, right? So B there, we're going to say option A is incorrect there. It will actually affect the reaction rate. Then B, using the same mass of what a powdered magnesium ribbon there. So we're using a powder, therefore it means now surface area is actually what's affected there. So in terms of what the surface area there, so it does do have an impact there. Then C, it says increasing the volume of the hydrochloric acid, right? So the most important term there, it says at the volume, right? So this one doesn't change the concentration of the solution, so it's volume there. So had we increased the concentration of this hydrochloric acid, yes, it was going to have an impact. Then option D says increasing the concentration, yes, this is what we're looking for, of the hydrochloric acid, right? So if we change the concentration of the hydrochloric acid, it's actually going to have an impact. Actually, it will affect the reaction rate. But however, our main focus is the one that will not affect, right? So will not affect. So it means our correct answer there is going to be option C, that increasing the volume of what? Of hydrochloric acid. Then we proceed to question 1.5, which reads, which one of the following statement is correct for a chemical reaction at equilibrium, right? So we need the statement that is correct for a chemical reaction that is at what? Equilibrium, right? So now we're saying the concentration of the reactants and the products remain constant. Which one of the following statement is correct for a chemical reaction at equilibrium, right? So it means now the concentration of the reactants and the products, they remain what? Constant, right? So here the concentration of the reactants and the products remain constant, right? Yes, this is the correct answer there. This is the correct answer that you're looking for. So to go through option B there, the concentration of the reactants is equal to the concentration of the product. This is also incorrect. Then the reaction is stopped. No. It's not, it hasn't stopped. Then option D is the number of moles of reactants is equal to the number of moles of the product, which is also incorrect. Therefore, the only answer that is actually correct there is going to be our option A, right? Then we proceed uh to question 1.6. So 1.6 reads there, solid sulfur, which is Sa there, reacts with oxygen O2 to produce sulfur dioxide. So we're given the reaction equation there, which is that one there. Then after that, now we're saying which is the correct Kc expression for the equilibrium constant for the above reaction. So we're looking for the Kc expression, right? So in terms of this Kc there, we're going to say our Kc is equivalent to the concentration of the products, right? So these are our products there. I'm going to say concentration of our products, which is SO2 there, then the exponent of what? Of 8 there, right? And then all over the concentration of our reactants, right? So it's going to be concentration of what? 8 O2 there. O2, which is a gas, right? And then to the exponent of what? Of 8, right? So let's take note, when it comes to this Kc expression, we do not include what? Solids and what? In liquids. Therefore, we are not supposed to add this one, right? So we are going to look for an option that is actually going to match with this one. So the one that actually matches with this one is option B. This one is correct, right? This one is incorrect because what they do, they also included the concentration of a what? Of a solid, right? So we do not include the concentration of a what? Of a solid. And then this one again is incorrect. They started with reactants at the top, then products at the bottom, and then this one also SO2 there. They forgot to put the exponents there. It was supposed to be an 8 and an 8. So if it's like this is actually going to be what? To be incorrect then. Then we proceed to question 1.7. 1.7 here we're asked to, according to Arrhenius theory, what is a base, right? So according to Arrhenius, a base is a proton acceptor, right? So it means now our option there for 1.7. Okay, so Arrhenius, Arrhenius, not according to Laurie Bronsted, sorry, it's Arrhenius, right? So it means our option A there, a proton donor is an acid. This is an acid according to what? Acid according to Lowry Bronsted, right? So Bronsted Lowry. So I'll just like say LP there, and then a proton acceptor. This is a what? This is a base according to who again? According to Bronsted Lowry. Okay, or Lowry Bronsted there, right? Then our option A and B are already wrong, right? Then we say option C, right? So option C reads a substance that dissociates in water to form a H plus ion, right? So this is an acid according to what? To Arrhenius. Then the option that you're looking for might be D. So it says here D, a substance that dissociates in water to form OH what? Ions, right? So this is the one that we're looking for, a base, right? So the correct option there is going to be option D there, right? Okay, to proceed to 1.8, it says consider the reaction below, right? So the reaction below is this one there. Then we're saying which one of the following are two acids are in the above reaction, right? Basically, for us to be able to do this, we're going to like quickly pair them, right? So here we're going to look for a substance that has got a difference of what? Of an H plus, right? So I'm going to compare this from the reactants with the products, right? So I can see here the only change between this and that, right, is the H plus, right? So can you see here I'm having H2, here I was having H3, right? So those are actually going to formulate my acid base conjugate pair. And then this one already you can see is supposed to pair with that one because now the only difference there is an what? Is an H plus, right? Hydrogen there. So according to this is my acid there, because an acid according to Arrhenius is a proton donor. According to Laura Bronsted, is a proton donor. So therefore, this is my acid there, right? So automatically making this one my base there. So this one again, remember I'm supposed to have an acid and a base on the same side. So this one is going to be what? A base there. And then on this other side, I'm going to have what? An acid, right? So now it means the things that we are looking for, they are our what? Our acids there. So according to this one is the acid, right? And then the other acid is on this other end, which is that one there. So let's look for the option that actually matches those two options. So it's H3, it's going to be our option C there, right? So can you see option C is H3PO4 and H2CO3 there, like that, right? So the correct option there is going to be option C, and then the rest of these are actually what's incorrect there. Then to proceed to the next question, so the next question reads there, a galvanic cell is constructed from cadmium and nickel, and then what is the correct notation for this cell there, right? So according to this now, we are supposed to start with the anode and then followed by the cathode, right? Okay, so it's supposed to be the anode, and then after that at the end here we're supposed to also have the cathode there, right? So if we're to go through these tables there, let me just like check there from our tables what we are going to have there. Let me just like scroll down there a bit for our tables there. Okay, so now what I'm looking for there according to this is our Ni, our cadmium, and our nickel there, right? Okay, so our cadmium there is going to be our Cd, right? Okay, so I'm looking for a Cd there, a Cd. Let me scroll a bit down, a little bit down there. Okay, so this is my Cd there. This is what I'm looking for, and then my Ni again, right? So this is what we are having there. Can you see this one is actually like least negative there, and then this one is actually going to be what more negative there, right? So according to the list that I'm actually going to have, right? So it means now my anode there is going to be this one is going to be the anode there, right? So and then this one is actually going to be the anode, and then this other one is going to be what my cathode there, right? Okay, so according to this I'm supposed to start with a Cd, then end up with my Ni there, right? So to go back to this here, what we're having there, remember if I'm to write my Cd there, let me just like copy this equation as it is. Cd2 plus 2 electrons, right? Cd2 plus, so we're having a Cd 2 plus 2 electrons to give me a reversible reaction of what a Cd there, right? So the other one, it was Ni, there is Ni2 plus again plus 2 electrons to give me a reversible reaction of what of Ni, which is a solid there, right? So yeah, just to confirm, that's what we are having there. Okay, so now in terms of this, right? So remember we identified the one that is the anode there, which is our Cd, right? So if we're having that Cd there, it means now we're supposed to write flip it around, right? So this is the anode, right? So just remember you flip the anode, right? So what I'm going to have here is a Cd, then after that I'm going to say a single arrow there, therefore Cd, then I'm going to get a Cd2 plus what 2 electrons, like that, right? So in terms of this now, what I'm having there, I will erase the one for the anode there. After flipping it, then I'm going to look for the other half equation for the what, for the Ni, right? So for the Ni there, we're going to write something like this, which is Ni 2 plus, and then plus 2 electrons, then to give me a single arrow, and then it's going to be my Ni, right? So remember I said I'm supposed to start with the anode, then the cathode. So it means now I'm going to start with the Cd. So the options that actually start with Cd there, we can see already it's C only, right? Not Cd2 plus. So it's Cd, then another one again for Cd2 plus there we have. Then after that we go to the cathode, which is this one. Can you see we start with our Ni2 plus, then we end with what, our Ni there. So it means our correct option there is going to be option C. That's the correct option that we are looking for. Then to proceed to 1.10 there, which reads, which one of the following half reaction takes place at the cathode, right? So the main focus is going to be our cathode, right? So remember, of an electrochemical cell, use 2 electroplate and ion spoon with what, with silver, right? So remember here at the cathode, what do we have there, right? Okay, so reduction takes place at the what, at the cathode, right? Reduction takes place at the cathode, right? So how do you actually define reduction, right? So reduction in terms of electrons is the gain of electrons, right? So which is the gain is the gain of what? Of electrons, right? I'll just write E negative there. So we're gaining electrons, right? So if we're gaining electrons, what does that mean? It means now we're going to say our option A there, right, is the correct answer for the what? For this silver. They're going to say cathode and electromagnetic silver spoon, right? This is the silver spoon, right? So it means here, what are we doing here? We are gaining electrons, right? So can you see here that silver He plus now is gaining these what? These electrons to formulate what? Your silver. So our option A is the one that is actually going to be what? The correct option. C and D are more of outliers because they are talking about what? The ion. Then this one here is the reverse, which is the opposite, right? So this is the opposite. So it's actually what's incorrect. So our correct option there is going to be our option A, where we're looking for the gain of this what? Of these electrons. So we're gaining these what? These electrons. Then we proceed to question 2, which is now our structured question there. So question 2 reads there, it says the letters A to E, the letters A to E. So the letters A to E, the letters A to E in the table below represent 6 organic compounds, right? So we're having these 6 organic compounds. Then after that now, we're asked to write down the letters representing a compound with the general formula CnH2n-2, right? So here we are, CnH2 n-2. So this basically is formulates an alkyne, right? So it means we're looking for an alkyne in terms of this here. It's an alkyne, right? So an alkyne has got what? A triple bond, right? Alkyne. He has got triple bonds, right? So let's look for something that has got a triple bond, right? According to my analysis, this is the one that we are looking for, which is our option B, because B has got what? Triple bonds within that part there is where we're actually going to have our triple bond there, right? Then to proceed there, they're saying a ketone, right? A ketone is actually identified by this functional group, which is referred to as our carbonyl group, right? So it means our option there is going to be option D, because this is where we're actually having our what? Our carbonyl group then. Then we proceed to 2.1.3. There it says a compound that can be used as a fuel, right? So we usually break down these large alkanes, right? To formulate what? Smaller consumable I can just say hydrocarbons. We use hydrocarbons as what is fuels, right? So we're having our option A and our option B, which are our what? Our hydrocarbons there. Okay. So we're having our hydrocarbons there. I'm going to say my hydrocarbons there, which is my A and D, right? So my answers are A or D, right? So you can choose either one of them there, right? Then to proceed there, it says here after that it reads here an unsaturated hydrocarbon, right? So unsaturated there, it means we are having multiple bonds between what carbon to carbon what atoms, right? So therefore the only one that has got multiple bonds between carbon to carbon atoms is option what? B. So the correct letter there, I'm automatically going to write the letter B. Then to proceed to question 2.2, which reads for compound E, write down the name of the functional group, right? So name of the functional group, and you are focusing on compound E, right? So this is our compound E, which is our butanoic acid, right? So butanoic acid there, the compound, the name of the functional group there is referred to as the what? The carboxyl group, right? Okay, carboxyl group, like that. Okay, so that's how we identify the name of this what? Functional group, which is a what? A carboxylic acid, right? From a carboxylic acid, their functional group are referred to as a what? A carboxyl what? Group, right? Then also on E, we're asked to write down the structural formula of its functional isomer, right? So we're looking for a functional isomer, right? So for a functional isomer there, it's just a matter of us changing a size there. Remember, the number of carbon atoms won't actually change. Usually when it comes to functional isomer, carboxylic acid usually go with what? With esters. Therefore, I'm going to draw a structure of an ester there. I'm going to say one there, maybe start with my hydrogens there, bond my hydrogens like that, like that. Then after that, I'm going to say C again, the one that now formulates this ester. It's going to be C double O, then C double bond O, then C again. Then I'm actually going to retain my number of what? Of carbons there, which is, I mean, two of them. Since we're having a four, Therefore, remember the number of carbons, they do not change. They should always remain what? The same, right? So this is how I was actually going to what? To write down the structural formula of the functional group of this question. So the answer there for 2.2.2 is that one there. That's the structure they are actually looking for. Then to proceed to question 2.3, it reads here, write down the IUPAC name of the compound C, right? So we're looking for the IUPAC name of compound C, just to scroll up there to compound C, right? In terms of counting, right, remember we're supposed to count from the side that is closest to the substituents or the branches, because this is a haloalkane, right? So in terms of this, if I'm to count here, I'm going to say carbon number 1, carbon number 2, carbon number 3, then carbon number 4. What does that mean? So this one becomes my side chain or my substituent. So 4 or 5, 6, 7, and 8, right? So it means now I'm having the longest chain as 8. But if I decided to count on this side, right, I'm going to say 1, 2, 3, 4, 5, right? Can you see now, if I'm to count like this, it means now the substituent is actually going to have what? A higher number there. So the correct numbering should start at the top, then going way downwards, right? Having said that, now allow me to just like erase all these other numbers there at the bottom. Then now we know on carbon number 4, we are having that methyl group, and then on carbon number 3, we're having also that chloro there, right? Or our halogen there, right? So it means now in terms of this 1, 2, 3, 4, or 5, okay. 1, 2, 3, 4, 5, 6, 7, 8, right? So the longest chain is actually going to be 8 there. Okay, so on carbon number 3 and on carbon number 5, we're having this chloro. This chloro, let's take note of that. We're having this chloro, right? It means here I'm going to say which one comes first, the chloro and the methyl alphabetically is going to be the chloro. Therefore, I'm going to say 3 on carbon number 3, I'm having a chloro, and then on carbon number 5 also, I'm having this chloro. So it's carbon number 3, that one, and carbon number 5, I'm having a chloro. So in total, I'm having 2. Therefore, I'm supposed to say dichloro. Then after that dichloro, then on carbon number 4 here, on this carbon here, 4, I'm having this what subchain or this substituent, which is more of an alkyl group, and then the name of it is a methyl. So I'm going to say dash. Remember the letters and the numbers, you separate them with a what? With a hyphen. Then I'm going to say methyl, and then the longest chain there is 8 carbons, which is our octane, right? So the final name is going to be like that. So the final name there is going to be 3,5 dichloro 4 methyl octane. So that's our answer there for compound C, which is our IUPAC name there. Then to proceed to, again, we are asked to write down the IUPAC name of compound D, right? So let's look at compound D and see what we have on compound D, right? So on compound D, what we're having there is a what it's more of a ketone, right? So it's a ketone, right? Remember the suffix for ketone is on, right? So in terms of this, let's count the longest chain. There is 1, 2, 3. We're having 3 carbons, therefore it's prop, right? So I'm going to say propan dash 2 on, right? Dash 2 on, right? Okay. So sometimes it can also be written as what? Propanone, right? Propanone, like that, right? But I prefer this one, which is propane 2 dash on, right? So that's our ketone there. So then to proceed to the next question. So the next question, which is our 2.4, it reads there. Write down the IUPAC name of the functional isomer of D, right? So write down the IUPAC name. So we're looking for the IUPAC name of the functional isomer of D, right? So it's a functional isomer of which compound, which is D, right? So in terms of this day, we're going to have remember ketones, they go along with what with aldehydes, right? So it's a matter of us changing this functional group and then putting it where. So we're going to move this functional group and put it where at the end there, right? So remember hide aldehyde, they like to hide where at the end there. So having said that, now it means now I'm going to have the same number of carbons there, which is 3. Then I'm going to say proper null, right? So proper null. So it's going to be, this is the name of the what? Of the isomer for what? Or functional isomer of what? Of D there, right? Then we proceed to question 2.5, which is write down the structural formula of a chain isomer. So we're looking for a chain isomer of compound A, right? So first thing we need to do is to look at compound A or structure A, which is A there. We're given A is our butane, right? So let's just like scroll down there to this part there. So it means here the original, what we're having a butane, right? And then after that, now we're looking for the chain isomer of this, right? So remember, same molecular formula, but different what chain there, right? So it means now the longest chain, I'm going to change it to 1, 2, 3, right? To 3, and then put my other carbon this side, right? So can you see it's still how many carbons? Total is 4, but now the chains are the ones that are actually what different. Therefore, I'm going to add another hydrogen there, hydrogen like that, hydrogens. Please do not forget these hydrogens. Always add them. Remember, carbon bonds how many times? 4 times. So it means basically what we are having here is 2 methyl 1, 2, 3 propane, right? So it's 2 dash methyl propane, right? Okay, so this is the functional isomer or the chain isomer of what? Of compound A. Then they are saying here again, write down the structural formula of compound E, right? So let's look at our structure E and see what we have there. For E is a butanoic acid, right? So butanoic acid, right? So having a butanoic acid, now it means we are looking for that structure. They're saying what we should write down the structural formula of compound E, right? So if it's butanic acid, it means we're having a total of how many carbons? 4 carbons. 1, 2, 3, and then 4, right? So to make it an acid, it must have an OOH, right? So which is our functional group, like that carboxyl group, right? So this is the final part. Then after that, now we're supposed to add our hydrogens like that. Hydrogens, 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 hydrogens. So this is the structural formula of what? A butanoic acid, right? Take note of the functional group there at the end, which is our COOH, like that, right? Okay, so then we're going to proceed to question 3. So question 3, there is the vapor pressure of two organic compounds at a specific temperature are compared, right? So at a specific temperature are actually what? Compared, right? So now we're having our butane there and then methyl propane, right? Molar mass is almost comparable, which is the same. They've got 60, 58 grams per mole. Then the first question there is they were supposed to define the term vapor pressure, right? So let's define the term vapor pressure. So vapor pressure is defined as the pressure exerted by, I'm going to write it down, the pressure exerted by a vapor, a vapor at equilibrium, at equilibrium with its liquid, its liquid in a closed system, closed system. Okay, so please make sure you master these definitions, and then I will actually like underline some of the keywords that we need there. So your definition should actually contain the pressure there. Then after that, exerted by a vapor, it's equilibrium with this liquid in a what? In a closed system, right? Take note of the word closed system there. We do not use isolated system in terms of paper 2. We use the term what? Closed system. Then we proceed to 3.1.2. So 3.1.2 reads which one of the two compounds has the highest vapor pressure, right? So we're looking for the one that has got the highest vapor pressure, and then we're asked to only write A or B, right? So according to our analysis there, which one is actually going to have a highest vapor pressure? So it means our option is going to be option B. Then here we're actually going to explain here why we're saying our option B is the one that is actually going to have a highest vapor pressure. Then 3.1.3 says I fully explain the answer to question 3.1.2. So we're supposed to what? To explain this answer, right? So I'm going to like use this space on this other end there to explain what is actually happening there. So in terms of that, I'm going to say A, which is our compound A there. A has a largest surface area. A has larger surface area. Then I will say the second point there is going to be say, therefore, if it has got a larger surface area, it means now it has got stronger intermolecular forces. Therefore, it's going to have stronger intermolecular forces, stronger intermolecular forces. Then the last option there is going to be say more energy. So more energy is needed to overcome, is needed to overcome, needed to overcome, intermolecular forces, intermolecular forces. Okay, basically, what does this mean? So it means here in terms of A, so if we're having more energy that is needed to overcome intermolecular forces, it means here this one is going to be having what? A high boiling point there. Okay, so they're saying here, fully explained to the answer 3.1. So it means it's going to be having a higher boiling point, right? So high boiling point there, and then automatically its vapor pressure is going to be what? A low vapor pressure, right? Okay, so it means the other one there, which is our option B, is actually going to be having, in terms of the vapor pressure, it's actually going to be having a highest vapor pressure and a low boiling point, right? Then after that, we proceed to question 3.14. Says give a reason why the above comparison can be considered as being fair, right? So what's the reason why these are considered as being fair? Because now, if we were to look at this molecular formula there at the top, right, we can see that it's actually what 58 for both of them, right? So I'm going to say the same molecular mass, right? Okay, sorry, same molecular mass instead of formula there. So I'm going to say the same molecular mass. Okay, so my first option there, same molar mass, right? Okay, I'm going to say same molecular mass, like that. Okay, then the second option I can say, oh, if we look at these, all these are actually what? Alkanes, right? So it means now they belong to the same homologous series, right? So I'm going to say same homologous series as option number 2, same homologous series. Therefore it means these are actually what are comparable there. Then I'm going to proceed to question 3.2, which says the compounds propane 1-ol and propanol, right, compared, which compound has a higher boiling point, right? So we should to specify which one is going to have a higher boiling point, and then after that we need to fully explain our answer. Then we're going to make use of this other space here. So we're comparing propane 1-ol with propanol, right? The other one is an alcohol and the other one is a ketone, right? So according to this here, I'm going to say 3.2 there. We're having our question 3.2 there. I'm going to say propane 1-ol. So I'll start with propane 1-ol. Propane dash 1-ol is the option, right? So is the answer. So the one that is actually going to have a higher boiling point is going to be propane 1-ol, right? So that's the answer there. Is propane 1-ol is going to have a higher boiling point, right? So, okay, so then after that, I'm going to say again now in terms of my explanation there, I'm going to say propane 1-ol has hydrogen bonds. So I'm going to say propane 1-ol has hydrogen bonds, right? So it's going to be hydrogen bonds, right? So that's the first part. Then what about propanone there? So in terms of propanone, what we have, propanone has got dipole forces. Propanone has dipole or dipole forces, right? And then I'm proceeding to the next point then in terms of the comparisons in terms of this, right? So intermolecular forces, I'm going to say intermolecular forces. Allow me to write IMF. Please do write this in full as intermolecular forces. Okay, in propane 1-ol, in propane 1-ol, in propane 1-ol are stronger than those, are stronger than those, are stronger than those in propanone. Okay, so propanone, like that. Okay, then the last bullet there I'm going to take in terms of what? In terms of energy. So I can just say more energy is needed to overcome intermolecular forces. More energy is needed to overcome, overcome. Allow me to say IMF, right? In hydrogen bonds, then in what? Hydrogen bonds, than in dipole forces, like that. Okay, so this is how we're supposed to attempt this question. Then I'm going to proceed to the next question, which is the 3.3. Question 3.3, it says the table below shows the results of an investigation regarding the melting points of organic molecules, right? So we're given those organic molecules A to C there, right? Then they are asked to write the independent variable for this investigation, right? So the independent variable for this investigation is going to be what? Okay, so let's look at what changes there, right? So it means here we're having a butane, AAE, all these are alkanes, right? So, but in terms of this, what is actually changing? The type of branches. Can you see? So it's going to be what our independent, what our variable there. So it means here, the one that is actually going to say the independent variable, we're actually going to say branching there, right? So branching is the independent what variable, right? So the dependent variable there is going to be what our boiling point there. Okay, so now we're asked to explain the trend in boiling points of for the above what investigation, right? Okay, so now I'm going to formulate a trend and just say from A to C. Okay, I'll just say from A to C. Okay, so what's happening from A to C? Then after that, I'm going to say here, uh, less branching. Okay, I'm going to say less less branching. Okay, then after that, I'm also going to say less branching and then stronger intermolecular forces. Now it means as we are going down the group, our intermolecular forces become what? Stronger intermolecular forces, stronger intermolecular forces. Then after that, what we are going to talk about is energy, right? So I'm going to say more energy is needed to overcome intermolecular forces in A, intermolecular forces. More energy is needed to overcome intermolecular forces in what? In C, sorry, in C, molecular forces in C than in what? Than in A, like that. Okay, so this is our answer for 3.3 there. Can you see that the boiling point is actually what's higher there, and then this one is actually what's lower there, right? So it means now we need more energy in what? In C compared to what? To A there, right? So you just like formulate a trend. Do not compare A versus B, then B versus C, then C versus A. Just formulate a trend, say from A to C, right? So can you see the branches, they become less and less as we are going down the group like that, right? So it means now what happens there? It means our intermolecular forces, they become stronger. And then what if they become stronger? What happens there? It means now we're going to need more energy to overcome them. Then we proceed to question number 4. So question number 4, they were given a flow diagram which shows the preparation of different organic compounds from this is the one that you're given there, CH3, CH2, CH3. Then X, Y, and Z represents what? The organic reactions there, right? So this is the table or the flow diagram that we're given there. Then it says write down the type of reaction represented by reaction X. So to focus on X there, so we started with something there to give us compound A, right? So in terms of compound A, then what are we going to have there? Okay, so we're going to say from A to this, right? To an alkene, right? So to an alkene, there is going to be what? Elimination, right? Okay, so I'm going to say the first one there is going to be what? Elimination. We are eliminating elimination, right? Okay, so why do I say elimination? You can see here we started with what? With something that is actually saturated here. So it's something that is actually going to be saturated, right? So here we're actually having what? Something that is actually what? Unsaturated, right? So remember, we're using the term saturated loosely, especially it comes to this what? Compounds, right? But generally, we're saying here there's actually going to have what? Single bonds. Then here we're having double bonds. Therefore, this type of reaction there should be what? Our elimination reaction, right? Then for Y, the compound Y there, what is happening for Y, for reaction Y there? So we started with something that is saturated again. It has got single bonds, and then also we're having an alcohol there, which is also our single bonds. So alcohols, they do actually have what? Single bonds there, right? So if we started with something that has got a single bond and ended up with something that has a single bond, this one is going to be referred to as what? Our substitution, right? Substitution, substitution. Okay, so because now there is an alcohol that is actually formulated there. So basically what I know is that basically the general reaction, if I was to be specific in terms of this, I was going to refer to as being hydrolysis, like that. Okay, so it's a hydrolysis reaction. Then we also have our reaction Z there. So this is our reaction Z there. Can you see there's also our sulfuric acid there, S2SO4, to formulate and what? An alkene. So we started with something that has got single bonds, and then now we ended up with something that has got what? Double bonds, right? So it means the type of reaction there is actually going to be what? Our elimination, right? So elimination reaction, right? So then to be specific in terms of elimination, what type of elimination do we have there? I'm going to say is dehydration, right? So it's dehydration. Okay, then we proceed to the next question. Then they are saying reaction X takes place in the presence of a strong base, right? So reaction X there is a strong base, right? Can you see the strong base is our sodium hydroxide there, right? That's a strong base. Then they are saying here, write down the IUPAC name of the compound A. So the compound that is actually going to be formulated at A there, right? So we're looking at this here. What is it that is actually going to be formulated at A, right? So it means here what we are going to have here is 2-bromo-propane, right? So we're going to say 2-bromo-propane, right? So it's 2-bromo propane, 2-bromo propane, like that. Okay, this is what you're going to have there in terms of this 2-bromo or propane, right? Then after that now, so it's just the name there. IUPAC name is going to be 2-bromo propane, right? Propane. Okay, so you can see it's a halo alkane or an alkyl halide, right? So now they're saying balance the equation for the reaction X using structural formulae, right? So now we're looking for the equation X there, this one from here to that one, using our structural formula, right? So already we know we're having our 2-bromo propane. So it means prop means how many carbons? 3 carbons there. Allow me to write here, try to squeeze it there. 1, 2, 3. And then carbon number 2, we're saying we're having a bromo, which is my Br there, right? So this is what I'm having. Then the rest there, I'm going to add my hydrogens like that. Hydrogens, please do always include all these hydrogens, and always remember your carbon always bonds how many times? 4 times, right? So what did we add there? We added this sodium hydroxide, right? So it is a strong base there. I'm going to say sodium hydroxide, NaOH, right? So now what are we going to have is our product. Allow me to write it underneath there. So it's an arrow. Then let me just like change color to show the product there. So my product there is going to be what? A double bond, right? So can you see it's an alkene? So an alkene there, what type of an alkene? The number of carbons, they do not change. So I'm going to have 1, 2, and then after that I'm going to say 3, right? So for us to formulate an alkene, it means here this bond there is the one that we're actually going to what? To eliminate there, right? So it means now we're going to have a double bond instead of what? Of a single bond. Then after that, you're going to add our hydrogens like that. Hydrogens there, hydrogen at the top there, and then another hydrogen, then hydrogen again here. So always remember your hydrogen should bond how many times? 4 times, right? So it means now we're left with something again. It means now I'm going to say my NABR plus my what? My water there, my H2O, right? So this is how we're supposed to like to go about it, right? So in terms of like the balanced equation for the reaction of what? Of compound X there, right? So it means now what did we start with? We started with this haloalkane, which is our 2-bromo propane. Then we added to what? Sodium hydroxide. And then what do we formulate there? We are going to say it's an elimination reaction, right? What did we actually eliminate there? So it means we eliminated this hydrogen there, this Br, as well as a what? A hydrogen, right? So which hydrogen there? This hydrogen there, right? So we eliminated those. Then after that, now it means now we are actually going to formulate that double bond there that you see there. Then after that, the sodium and the bromine, it means this Br, they're actually going to what? To formulate a bond to make us what? An NABR. Then this hydrogen hydrogen also is going to attach to this OH, formulating our what? Our H2O. So that's how we go about that equation. Then 4.2.3, they said write down the IUPAC name of the alkene that is actually being produced, right? So this alkene there that is actually going to be produced. So it's 1, 2, 3. So it's a 3-carbon chain. Therefore, it means now we're going to have an answer of what you got that one correct is going to be prop 1 in, right? So it's going to be prop 1 in, okay? So I'm going to say here what you're going to have here is prop 1 in there, propene. So I'm going to just like change color there and say prop dash 1 in, right? So because where do we actually have our double bond there on carbon number 1 there. So that's the answer for that question. Then to proceed to the next question there, it says 4.3 there, state two differences in reaction conditions for X and Y, right? So it means for X and Y, we're looking for differences in what? In reaction, two differences in reaction conditions for X and Y, right? So I'm going to start with X there. X there. So what's there in terms of X there? It means X, we're actually going to have a concentrated strong base, right? So for X there, we're going to have a concentrated strong base. Okay. So usually it's actually accompanied by what? By heat, right? So I'm going to say heat. But for Y, what actually happens there is that we are going to have a dilute. So for Y, we usually use a dilute strong base, okay? Strong base. Can you see the other one is concentrated and then the other one is just dilute, right? So instead of using heat, we're actually going to specify and say here with what? Mild heat, like that. So those are the two differences that we can have in terms of what? X and what? And Y. Then to proceed to 4.4 there, just to look at X and Y. So this is the one that we are having there, the X part and the Y part, right? So for Y there, for X there, we're saying what you are using there is concentrated what? Strong base. Can you see already you are having your sodium hydroxide as a strong what? Base, but it should be what? Concentrated, right? So here also we're going to have what? A strong base, but it should actually be what? Be dilute, right? So, and then in terms of the heat there, we say mild heat. And then here we are actually going to just say what? Heat. Okay, so this is what we're having as the differences between what X and Y. Then to proceed to question 4.4 says compound B is a secondary alcohol, right? So secondary alcohol, and then define the term secondary alcohol, right? So firstly, we define the term tertiary alcohol. Now we're going to proceed to define the term what? Secondary alcohol. So by definition, we're going to say secondary alcohol is when the C atom, so the C atom bonded the C atom bonded to the hydroxyl group Okay, so it's bonded to our main other hydroxyl is bonded to the C atom bonded to the hydroxyl group. Okay, let me add group there to the hydroxyl group is bonded to hydroxyl group is bonded to two other C atoms to two other C atoms. Okay, so that's how we actually what go about that question. Then we proceed quickly to question 5. There, so 5.1 reads glucose is metabolized in the human body through the following simplified equation. So this is the equation that is given there. Then the graph below represents the energy changes for the above reaction, right? Then what we are needed to do there is to like ask the first part. They're asking us, is this reaction endothermic or exothermic? And then we're asked to give what a reason for our answer. So we need to identify whether this is what endothermic or exothermic, and then after that you're going to say to give a reason for your answer. So it means here our type of reaction there is going to be what? Exothermic. So we're saying the answer there is exothermic. Okay, so exothermic, like that, right? So the reason there, automatically I can just say delta H is what? Less than what? 0. Or if I want to talk in terms of the energy, so you can see the energy of the products, these are your products, is actually what? Less than the energy of the what? Of the reactants there, right? Okay, so you can just say that as a reason but also you can just say delta H is what, less than 0, or delta H is actually what, negative. So those are your reasons behind an exothermic reaction, right? Then 5.1.2 says express the following in terms of the energy values A, B, and C shown in the graph, right? So the energy of the activated complex, right? So activated complex, remember, unstable transition from the reactants to the products. So it means here we are at the peak there. So at the peak there, it means we are going to have our value or symbol A. Remember, we're asked to indicate in terms of what, A, B, or C there, right? Then to proceed to 5.1.2, which is B, then the activation energy of the reverse reaction, right? So a reverse reaction is more of like a mirror of this one. So it means now our product is actually going to be here at the bottom, now becoming our reactants. Then our reactants are now our what, our product. So this is what we're having there, right? So the same thing that we're actually going to have there. So it means now the activation energy of the reverse reaction now is actually going to be from what, from A until what, until C. So we're going to say our answer there is A until what, until C. Then delta H for the forward direction, right? So delta H for the forward direction. So this is the forward direction, and then this is our reverse direction, right? So in terms of the forward direction there, it means now we're going to say products minus our reactants there. Remember, delta H by formula, delta H is equivalent to H products minus what, H reactants. H products minus what, H reactants, like that, right? So it means now what are we subtracting what from what, right? So it means here is actually going to be what, C minus what, B. So C is your product, and then B. Therefore, I'm going to say C minus what, minus B, like that. So that's how we're actually going to what, to get our answers there. Then we're going to proceed to 5.2. So 5.2 says in an investigation of a rate of reaction and excess to, so okay, so this is the excess sulfuric excess 200 cubic centimeters of HCl concentration. So we're given a concentration of 0.5 mole per dm cubed, reacts with zinc powder at STP, right? So standard temperature and pressure. Then the following spontaneous reaction. So it means it automatically happens, this one, right? So takes place then. After that, this is the reaction that is actually given. Then we're told the volume of the hydrogen gas produced is measured at regular intervals, and the following graph is actually what drawn, right? Then after that, now we're asked to define the term. So this is the graph that is actually shows like the volume of the hydrogen gas produced, right? Take note also, they're saying in what, in cubic centimeters then, and then this is the time in what, in seconds. Then we're asked to define the term concentration, right? So concentration is defined as the amount of solutes, so amount of solutes per unit volume, right? Amount of solutes uh, per unit volume, like that. Okay, so that's how we define our concentration. Then 5.2.2, it says write down the limiting reagent for the above reaction, right? So we're looking for the limiting reagent, right? So from the above here, I can just say, remember what I'm going to focus on is my actually what, my zinc and HCl, right? So to look at zinc there and HCl, right? So these are my reactants. So one of them should be a limiting reactant or reagent, right? So in terms of this here, can you see there, according to the top part there, it says excess. What is in excess? Excess 200 kilometers, cubic centimeters of solution, which is our HCl. So it means our HCl is in excess, therefore automatically making our zinc the limiting what, reagent. Therefore, I'm going to say, according to this, the limiting reagent is going to be my Zn, or what, I can write it in full as what, as zinc, like that. Then 5.2.3, they're saying calculate the mass of zinc that is used, right? So we're looking for the mass of zinc that has been what, been used there, right? So for us to calculate this, I don't know, let me just like use space here. I'm going to start with the number of moles of what, of HCl, of hydrogen gas that is produced, right? Because this is the volume that you are given there for the hydrogen gas, right? So I'm going to say the number of moles of hydrogen gas produced there is equivalent to what? To V all over Vm, right? So this is what I'm having. And then the volume that was actually given, that the one that is produced there, can you see, is 414,4 cubic centimeters, right? So it's in cubic centimeters. Remember, I'm supposed to convert that one to dm cubed, right? So for us, we're going to say 414, comma 4, then we divide by 1,000, right? So to get our answer in what, in dm cubed. So if we divide that one, we're going to get a value of 0, 4144 dm cubed, right? So always take note of the units of what? Of measurement. Here we are given in what? In cubic centimeters, right? So in this case, I'm going to say is equivalent to 0, 4144 all over the VM, right? So this is the molar gas volume, right, at STP, right? So we're given STP there, right? So the molar gas volume there is 22,4, right? So where do I get this from? We get it from our data sheet there, where we're actually going to have our VM, right? So can you see this VM there? So the VM at STP, right? So this is our STP, and then the value there is 22,4. Therefore, I'm supposed to divide by 22,4. So I'm going to say 22,4 like that, right? So if I do the math there, it's actually going to give me a value of 0,0185, 0,0185 moles, right? So these are the moles that I'm actually having in terms of what? Of the hydrogen, right? Then allows me to erase this other part there at the top. Then after this, now I'm supposed to use the mole ratio to calculate the one for what? For zinc, right? So I'm going to say here, according to my balanced equation there, I'm going to say mole ratio. So according to the mole ratio there, I can see this is zinc versus HCl, right? So zinc versus, sorry, my hydrogen gas is 1:1, right? Therefore, I'm going to say Zn there versus my H2 gas. So we have calculated the moles of the gas there. So according to the mole ratio there, balanced equation, this is 1:1, right? What does that mean? So if I started with 0, if I use 0,0185, automatically on this side also I should be using the same what number of moles. So it's 0,0185 like that. Therefore, now for me to calculate the number of moles of zinc there, I'm going to say number of moles of zinc. So N of what? Of zinc there is equivalent to M all over M, right? So what do we have therefore? This is the same as the mass that is actually given is what I'm looking for. But the number of moles I already have there is 0,0185. So I'm going to say 0,0185 is equivalent to M, right? All over the molar mass of what? Of zinc, right? So if you can just like refer to your periodic table, you'll find that zinc has got a molar mass of what? Of 65. If I'm not mistaken, there is our zinc there with a molar mass of what? Of 65. So we divide by 65, right? Then after that, we are supposed to make M the subject of the formula, right? So it means we are supposed to cross multiply. So 65 multiplied by that, we're going to get a value of what? Let's just do the math. Therefore, my M there is equivalent to 1,1,202525 grams like that. Okay, so this is the mass that is actually what needed there, the mass of zinc that was actually what used there. So that's how we attempt question 5.3 there, right? Then we proceed to question 5.4, 5.2.4. Then they say the same mass of zinc granules is used instead of what? Zinc copper powder, right? So now they're using what? Granules, right? So more of like granules. I don't know how to explain it, but it's more of like the peel part, right? There is the powder. Remember, there is the powder part, and then there is the more of what we refer to as a peel. So the powder and the peel is more of like the differences between these two. Then how will this affect the rate of what? Of reaction there, right? So how will this affect the rate of reaction, right? So choose increase, decrease, or stays the same, right? So it means now how will the same mass of zinc granules is used? Okay, so now it means we are decreasing the what surface area there, right? Our surface area is the one that is actually being what? Affected there. So it means now the correct answer there is going to be what? Decrease, right? So I'm going to just say decrease, right? So it's going to be a bit slower because now we're using granules instead of what? Of powder. Here we're actually having more reaction sites, right? In terms of the powder, and then here is now granules. It means we're having what? Less reaction sites, right? Then they are asking us to use the collision theory there for 5.24b. Use the collision theory, right, to explain the answer to question 5.2.4, right? So this is our B. This is how we're going to attempt our B there. So it means there is a decrease in surface area. There is a decrease in surface area. Okay, because now we're using what? Surface area. We're now using what? Our granules there, right? So what does that mean in terms of that? If we decrease the surface area, therefore it means less particles with what? Correct orientation. Less particles with correct orientation, correct orientation, orientation. Then after that, we're also going to talk in terms of what effective collisions, right? So if we're having less particles with correct orientation, it means now we're going to also have what less effective collisions. So less effective collisions, effective collisions, uh, collisions per unit time, per unit time. Okay, so this is how we attempt that 5.2.4b there. Then to proceed, 5.2.5, it says a suitable catalyst is used to the reaction mixture, right? So a catalyst, remember, there is there to speed up the rate of what? Of reaction, right? So now we're asked to redraw the graph above in your answer book and label the given curve as A. And then on the same set of axes, sketch the curve that will be obtained if a catalyst is actually what added, right? And then label this one at curve B, right? So what I'm going to do is just like more of copy that one down there. I just redraw it. So what I'm going to have there is like that. And then what was I having is time and volume of what? Time. I'm actually going to say time in seconds. And then here I'm going to have my volume again. Volume in terms of this, it was in cubic centimeters. I will leave it like that, right? So the first one that I'm going to start with is the one that I'm going to copy there, which is my A, right? So I'm going to write my A there. So my A is going to go up like that. Let me just like make it a bit less steep. Okay, so this is my A there. So it's going to go like that and then curve like that, right? So I'm going to call this one A, right? So the one with the catalyst there, I'm going to use a dotted line and a different color. So they will start from the origin, but this one is actually going to be what? A bit what? Steeper. Therefore, I'm going to say B, right? So take a note of the amount of product that is being formulated there, right? It remains the same. It's not affected, but what is actually affected is the rate of reaction. So a catalyst just speeds up the rate of what? Of reaction. So B, can you see, is more steeper than what? Than A. So B is more steeper than what? Than A there, showing that here the reaction rate is actually what? Is actually faster. Then we proceed to question 6. So question 6 reads there, hydrogen iodide, which is your HI there, hydrogen iodide is allowed to decompose in a 5 dm closed container, right? So at a temperature of 425 degrees, according to the following balance equation. So this is the reaction of hydrogen iodide to produce hydrogen gas plus iodine gas, right? Then we're told here, when the mixture reaches equilibrium, right, at 425 degrees, it is found that 0.02 moles of H2 is present in the container, right? So at equilibrium, we're having that 0.02, right? Then the equilibrium constant for this reaction is what? 0.016, right? So this is our Kc there. So we're given that one down there, right? So the first question there that we're given there, it says define the term closed system, right? So we're referring to the term closed system, right? So it's a system that is actually isolated from its surroundings. A system, we're going to say a system that is isolated from its surroundings. Okay, so this is the definition of a what? Of a closed system, right? So it means now they do not interact with the outside what? Environment, right? So then after that, calculate the initial number of moles, right, of HI in the container. Okay, so this is where we're actually going to make use of the rise table, right? So I'm going to say, according to this, allow me to use the space there at the bottom, right? So I'm going to say divide this into our main equation, 2hi to give me, so it's 2hi like that, to give me my hydrogen, which is a gas, plus my iodine, which is also what? A gas, like that. Okay, so this is what I'm having there is my original equation, right? So I'm going to make use of the rise table there. I'm going to like draw something like this. Okay, let me use the end part of this page there. So I'm going to have something like that. And then here I'm going to split it into 3 different parts there. Two, and then let's say the third one there, right? Okay, so here I'm going to say here I'm having my 2hi there, 2hi. Then here I'm also having my I2 like that, right? Okay, then the final one is let me just start with hydrogen there. I'm going to say my hydrogen there. This is my hydrogen, which is my H2. Then the last one is going to be my I. 2 like that. Okay, this is what I'm actually going to have then. Then after that, now I'm going to also formulate different tables there. Okay, so I'm going to say a ratio, the starting part there. I'm going to say my ratio. Then after that, I'm going to say initial moles, right? Initial moles, the moles that we started with, right? Then I'm also going to draw there, pardon my drawing, my lines a bit like not straight there. Then change in what? In moles, right? So we're going to say change in moles, right? This is my C there, which is my change in what? In moles, right? Then after that, now I'm going to proceed to have another one, which is my equilibrium moles, right? So this is my E part, right? So equilib, allow me to write just equilib moles there. Then after that, now I'm going to have the one at what? It's equilibrium, right? Okay, concentration at equilibrium. So this is the table that I'm actually going to have there. So I'm going to just like use square bracket to represent what? Our concentration. Okay, so this is the table that we are going to manipulate there, right? So after this, now we can actually try and plug in the values from the what? From the data that has been what? Actually provided, right? So to go back to here, it means here generally I can start with something like this, right? So at start here we're having this. It means there were no products, right? Okay, so according to the mole ratio, let's just like fill the mole ratio here is going to be 1 is to 2 is to 1 is to 1 like that, right? Okay, so what we know here is that we started with nothing there. So we started with our reactants. It means we did not have our products, right? So initial moles of these ones, 2, which are our products, I'm going to safely write 0 0, right? So we know along the way these ones are actually going to increase and these ones are actually going to what? To increase. So the change they were supposed to use a positive. However, on this other one, it means these ones, they're actually going to be used up to formulate our what? Our products. Therefore, I'm going to put a negative. Then here equilibrium moles now, and then the concentration there, right? So let's look at this. What are we given then? Here it reads here in the mixture, when the mixture reaches equilibrium at 425 degrees, it is found that 0.02 moles of what? Hydrogen is present, right? So where was it? It was at equilibrium. So these are the equilibrium moles of what? Of H2, right? So under H2 there, it means I'm going to write a value of what? 0.02, right? So according to this, what's the mole ratio according to this, right? So here is 1 is to 1. So if I use 0.02 this side, so it means here I should also have used something like 0.02, like, okay, so it's going to be 0.02. Then we leave it like that, right? So in terms of that, again, I can even ask that since we started with 0, then now we're having 0.02. What does that mean? It means we added how many? 0.02 again. And then here we started with 0, now we're having 0.02. Then therefore it means I also added, 0.02. Then having said that, now we are supposed to look at the concentration, right? Okay, so now let me just like employ my Kc expression there. Remember, Kc expression is equivalent to the concentration of my products, which is my H2 there, my hydrogen gas, multiplied by the concentration of my iodine gas, like that. Then all over the concentration of what? Of my Hi there, which is my reactant, right? Hi there. Then I'm supposed to square that one, right? Then also what am I given there? I'm given my value there, my value for what? The equilibrium constant. So the equilibrium constant there, can you see that we're given a value of what? Of 0.16 there. So that's my equilibrium constant there. So equilibrium constant is 0.16. It means my value for Kc there, I can say 0.16 there, right? So let me just like use a different color. Therefore, I'm going to say 0.16. 0.16, 0.016 is equivalent to, okay, so now what are we going to have there, right? So we need to get the concentration of these two, right? So remember how to calculate our concentration. Concentration is equivalent to the number of moles over a volume, right? So I'm going to start with this one here. I'm going to say concentration of what? Of hydrogen gas there is equivalent to the number of moles all over volume, right? Therefore, what do I have there? The number of moles is 0.02 all over the volume of this container, which we are told there at the top is, 5 dm cubed, right? So all over 5 there. So if we divide the 0.02 divided by 5, we're going to get a value of, let me just see there, 0.02 divided by 0 by 5. Okay, So I'm getting a value of 0,004, right? So it's going to be 0,004, right? Okay, so what is this? This is my concentration, right? So I'm going to say mole dm cubed, right? Okay, so this is the concentration I'm having there for H2, right? So I'm going to automatically write that one down, 0,004, right? So the same thing applies there. The same thing applies. The same thing applies. What are we going to have on this other end? It means now C is equivalent to what for I2 again. I'm going to do the same. So concentration of my iodine gas there is equivalent to N all over V, right? So the number of moles, can you see we still have the same, and then the volume is still the same. What does that mean? It means we're going to get the same value, which is 0,04, right? So I'm going to automatically write 0,004 mole per dm cube, right? So it means now we're having this concentration. So I'm having the concentration of this hydrogen and the concentration of this iodine. Therefore, I'm going to plug in their values at the top there, right? So it means 0,016 is equivalent to, I'm going to say 0,004, right? Multiplied by again 0,004, right? All over. So what am I having there? The concentration of my HI there. That's what I'm looking for, but I don't have it. Therefore, I'm going to say concentration of HI, then I'm supposed to what? To square it, right? So to make HI the subject of the formula, this is what I'm actually going to get there. So I'm going to say concentration of HI there. Allow me to just like make a shortcut there. So I'm going to say automatically root of, so to remove the square there, right? So it's going to be the root of 0,04, 0,004, which is multiplied by also 0,004, right? All over there. So all over what? So that's 0,16, right? 0,016, right? So if we were to do our math there, we should get a value of what? 0,0 316 like that, right? So this is the concentration that I'm actually going to have there, right? So which is 0,0316, right? So this is the concentration there, a mole dm cubed, right? Mole per dm cubed, like that, right? Okay, so that's the concentration of this one, right? So now for me to get my equilibrium moles there, so we need to say number of moles at equilibrium. How do I calculate the number of moles, right? So for me to calculate the number of moles there, I need to get to the concentration of HI, right? Okay, so by formula there, if I can just say concentration of HI, just to change color there so that there can be a demarcation there. So I'm going to say concentration there. What's the concentration, right? So I'm going to look for concentration of HI there. Why do I use this formula and all over V? Is because I'm looking for the number of moles, right? So I got my value for concentration there. So we said concentration of HI is 0,0316, right? Is equivalent to the N that I'm looking for. The volume remains the same, which is 5, right? So if we cross multiply there, we're going to get a value of 0,158, right? So these are the moles that we're looking for, the moles at equilibrium. So this is the value that I'm going to write there, 0,158, right? So we're having 0,15 moles, 58 moles like that, right? So now in terms of this now, for us to get here to the negative, then we are supposed to use the mole ratio, right? So the mole ratio says 2 is to 1, right? So if the mole ratio says 2 is to 1 there, in this side here for hydrogen, we're using 0,02. What does that mean in this side? It means on this side, we are going to use double. Therefore, I'm going to multiply 0,02 multiplied by 2. Therefore, I'm going to say my answer that I'm going to get is 0,04, right? 0,04, right? So mathematically, allow me to do it like this. So I'm starting with A there, and then I'm going to get my change there. If I subtract B there, I'm going to get the value of what? Of C, right? So mathematically there, if I'm to write it, A minus B is equivalent to what? To C, right? So now my A there, to make A the subject of formula, A is equivalent to C plus what? Plus B, right? So in terms of this, it means my C there is 0,158, 0,158. Then I'm supposed to add my my B there. So I was subtracting, since I actually transposed, it means it's a positive. So I will add 0,04, right? So my final answer there, if I add, I'm getting a value of what? Let me just quickly do the maths there. 0,04 plus 0,158 0,158. So I'm going to get a 0,198, right? So it means my answer there is 0,198. So the moles that I actually started with is 0,198 moles. So my answer there is 0,198 moles there, right? So that's how we actually attempt that question for 6.3 then we proceed to 6.3 there. It says, how will each of the following changes affect the amount of hydrogen gas produced, right? Only increase, decrease, or remain the same, right? So more iodine gas is actually like is added at this, right? So what will happen if we add more hydrogen gas, right? So it means here we're going to say the answer is decrease, right? So it's going to decrease. Why? Because we're adding more of the what of the I2, which is our product in this case. So it means now in terms of the reverse reaction, so here it means we increase the concentration of this, therefore the reverse reaction is actually going to be what? To be favored, right? Then after that, now 6.3.2, the pressure is increased, right? Let's look at this value there for pressure. So the pressure is actually increased. If the pressure is actually increased, what is going to happen, right? So the pressure, remember, favors the side with the least number of moles, right? Pressure favors the side with the least number of moles, right? So if pressure favors the side with the least number of moles, this is what is going to happen. This is what is going to happen. We're going to say, according to this, let's look at the number of moles. This side we're having 2, and then this side is 1 plus 1 also, which is equivalent to what? To 2. Therefore, in terms of this, if we are to increase pressure, it means now it's not going to have what an effect because the number of moles are equal on both sides, right? Therefore, the pressure is increased. It means our answer there is going to what? Remains the same, right? So it means here I'm going to say remains the same, right? So that's our answer there, remains the same. Then after that, 6,4, it reaches the 6,4 at 325 degrees. The equilibrium constant, which is your Kc for the reaction above, is 0,014, right? Is the reaction exothermic or endothermic? Then fully explain your answer, right? So the answer there is going to be our endothermic, right? So it's fully endothermic, right? So what do we do here? So let's look at this, right? At 325, was there an increase or decrease? So there was a what? A decrease, 0,014, right? We started with what at the top there? If I can just like erase there so that we can see. So we can see we started with what at Kc, they were having 0,016, right? So now it means what happened there? There was a drop, right? There was a drop in terms of the what? The Kc after we did what? We decreased the what? The temperature. So here it means our answer there we're going to say is endothermic. So our reaction there is endothermic, right? So it's going to be endothermic, right? Then to explain this, allow me to use this other space there. So this is question what? Let me just like see the 6.4. So we're going to say 6,4, 6,4 like that, right? So we're saying the type of reaction is endothermic, right? So this is an endothermic reaction, right? Endothermic reaction. Then we are supposed to explain what is actually happening there, right? So in terms of the endothermic reaction, we're going to say decrease in temperature, a decrease in temperature, decrease in temperature. What does it favor? Decrease in temperature. Favors an exothermic reaction. Not and okay. Favors an exothermic reaction. An exothermic reaction. Exothermic reaction, right? Okay, so this is our first bullet there. Then after that, now we're going to say here, Kc decreases with an increase in temperature. Therefore, we can see the Kc decreases with a decrease in temperature. With a decrease in temperature. Decrease in temperature. Okay, so this is what we're having there. Kc decreases with a decrease in temperature. Therefore, the reverse reaction is favored. So reverse reaction is favored reaction is favored. Okay, that's how we are supposed to attempt question 6.4. Then now we're going to proceed to question 7.1. We're going to proceed to question 7.1. Question 7.1 reads there, 7.1 reads there, 2 grams there of magnesium hydroxide is reacted with 30 cubic centimeters of sulfuric acid solution of concentration. So we're given the concentration of the sulfuric acid there, which is 1,5 mole per dm cubed according to the following balanced equation. So our equation is there. That's the direction there is actually balanced. Okay. So they are saying why is H2SO4 considered a strong acid, right? So this one is because it ionizes completely, right? So it ionizes completely. So I can just say it ionizes completely, ionizes completely. Okay, so at times they say in water to produce H plus what ions, right? So it produces H plus what ions like that. Okay, so then after that, calculate the concentration of the final solution, right? So we've been asked to calculate the concentration of the final solution, right? So I'm going to manipulate this other space here. So we've been asked to calculate the concentration of that final solution, right? Let me use a different color there. Okay, allow me to pick that one. Therefore, we're going to say what we're going to start here with there. What are we given, right? So we're given the mass of what magnesium there, which is 2 grams. Okay. Then also what we have there, we can get the number of moles from this, right? Since we know magnesium hydroxide is MgOH, right? So it means now we can get that one, right? So it means now we are going to start with the number of moles, right? So I'm going to say the number of moles of what magnesium hydroxide, which is MgOH, right, is equivalent to, okay, so I'm going to say M all over M, right? These are the number of moles, right? Therefore, here, what am I given? I'm given the mass of this magnesium hydroxide is 2. Then if we are to calculate the molar mass there, we're going to get a value of 58, right? So which is equivalent to, so if we do our math there, 2 divided by 58, 2 divided by 58, what am I going to get there? I'm getting a value of 0,03448, 0,03448, right? So these are our moles that we're actually calculating, right? So moles, right? So after that now, I'm going to use the mole ratio, right? So allow me to say mole ratio. So I'm going to say mole ratio there, right? Okay. So mole ratio between what? My H2SO4, right? Okay. So H2SO4 versus my magnesium hydroxide, right? So mole ratio there, I'm going to say H2SO4 versus the one for what? For magnesium hydroxide, which is my MgOH, like that, right? Then after that now, what does that mean? It means according to the balance equation there, we can see it's 1 is 2 is to 1. There is 1 there, and then is 1, right? So it's 1 is to 1. Then after that now, I'm going to say, so the number of moles that actually reacted, right? So I'm going to say reacted moles there, reacted moles, the number of moles that actually reacted there. Since we're having this one for 0,03448 is for magnesium hydroxide. So it means here we're also going to have what the same because the mole ratio there is the same, right? 0,03448 like that. Okay. So this is the mole ratio that you're going to have there. Then after that now, it means now I can actually calculate the initial number of moles of what? Of H2SO4, right? So then N initial, I can say initial H2SO4, right? H2SO4, right? So how do we calculate the number of moles, right? So according to this, if I can look there, I'm already given what the concentration. I also have what the volume there, right? So it means according to this, remember your C is equivalent to N all over V. So automatically I made N the subject of the formula there, right? So which is equivalent to C multiplied by what? By V there, right? Therefore, now we are going to say the concentration that I'm given according to this there is 1,5 mole, right? So per dm cubed. So it's going to be 1,5 then multiplied by the volume, right? So the volume there, can you see, is 30 cubic centimeters. And which volume should I use there? It should be in dm cubed. Therefore, I'm going to divide that one by 1,000. So if I can say 30 divided by 1,000 there, I'm going to get a value of what? 0,03, right? So it means here I'm going to say multiplied by 0,03, right? So if we do the math there, we're going to say multiplied by 1,5. I'm getting a value of 0,045, right? Okay, so I'm getting a value of 0,045, right? So 0,0, I can just say 0,045, right? Okay, so if you can round it off, it can be 0,05, right? Okay, so if I can just say this is approximately 0,05, 0.05, right? So these are the moles that I started with, right? So moles there. Then after that now, it means now I need my final moles of what? Of H2SO4, right? So I can say N final moles of what? Of H2SO4, right? So is equivalent to, so for you to get the final there, you're going to say initial moles minus reacted moles, right? Reacted moles, right? So if I have that one down there, then according to this, my initial moles are these there, which is 0.005 there, then minus my reacted moles. Where do I get them there? So it's at the top there, right? So these are the reacted moles there, right? So it means I'm having minus 0.03, right? So if I can do the math there, I'm going to get an answer of this is equivalent to 0.02 moles, right? If we subtract 0.05, let me just like write it close there, so that we can see that we are subtracting. Therefore, this is was 0.05, therefore minus 0.03, you're going to get a value of what? 0.02 moles, right? Then after that now, it means now we can calculate what we asked there. They're saying that calculate the concentration of the final what? Solution, right? So to get the concentration there, I'm going to say your concentration is equivalent to, so the concentration of my H2SO4 there, concentration of H2SO4 is equivalent to N over V, right? Number of moles over volume. Therefore, the number of moles is 0.02 all over the volume, which is 0.03. Remember, we're given the volume as 30, therefore we converted it what? To dm cubed there at the top there, when we divided by what? By 1,000, that part there, right? Therefore, if we do the math there, we're going to get a value of what? 0.6767 mole per dm cubed. Okay, so this is the final concentration that we're actually having in terms of this. So our answer there should be 0.6767 mole per dm cubed, like that. Okay, then we proceed to 7.2. So 7.2 says a dilute HCl solution has a concentration of this, so we're given that, and then the dilute solution reacted with the concentrated solution of what? Sodium carbonate, and then define the term dilute acid, right? So for the term dilute acid, we are saying that it actually contains, this acid contains a small number of moles of acid, right? So it contains an acid that contains a small number, a small number of moles of acid, of acid. So we're comparing it what in proportion to the volume of water, in proportion to the volume of water, like that. Okay, so this is how we actually like define that part there for 7.2.1, right? Then 7.2.2 there, it says here, calculate the pH of this HCl, right? So according to the formula, I'm going to start with the formula on this other page here. I'm going to say, let me change color to blue there. Then according to the formula, pH is equivalent to negative log concentration of what? H3O plus what? Ions, right? So now if you look at this here, we already given the concentration of the what? Or 0.5 of what? Of this HCl, right? So in this case, a take note also, my H is actually monoprotic, right? So like this HCl. So if we were to say it ionizes there, it's actually going to give me my actually HNCl, right? So automatically it means here the mole ratio is 1:1, right? So we're looking for the concentration of this H plus or H3O plus, right? So H plus and H3O plus can be used interchangeably, right? So now we're given the concentration of this, right? 0.015, 0.015, right? So therefore is 2 the same as 0.15. Okay. Oh, okay. So take note, whenever it's monoprotic, right, we are actually going to automatically plug this value here, right? But if it's diprotic, we are now supposed to use what? The mole ratio. So to proceed there, I'm going to say minus log, therefore, what's my concentration there is 0.15. Therefore, remember, I'm no longer supposed to use the square bracket there. I'm going to 0.15 like that, right? So this is equivalent to then my pH there. So if I can just say minus log bracket there, 0.15 there. I'm getting a value of what is equivalent 0.82. So my answer there is 0.82, right? So remember, pH does not have your units there. So that's how we are going to answer it like that, right? Then to proceed there to the next question, which is 7.3. A solution is made by dissolving sodium carbonate, which is solid, in water, right? So then is the solution of sodium carbonate acidic or what? Basic. So we know this is sodium carbonate, so it has to be what? To be basic there, right? Then after that, now they're saying write down a balanced chemical equation that explains the answer in question 7.31, right? So to write this one down there, we are going to refer to the carbonate, right? So the carbonate is written as CO 3, 2 negative, right? 3, 2 negative. And then since we are adding it to what? To water there, right? So I'm going to say plus H2O. So plus H2O. Therefore, it's supposed to give us a reversible reaction there. A reversible reaction of what? So if we add there, it means now our oxygen, one of the oxygen is going to come and attach where? Okay, so having that, it means now we're going to have our carbon attaching there. Therefore, it means I'm going to have a HCO3 negative, CO3 negative, right? So it means that hydrogen there attached itself to what? To the carbon there, right? And then plus, what are we going to be left with? So since we gave out one H there, it means now we're going to have what? A hydroxide, right? So plus OH, right? So OH negative, right? Then to put the solutions, the state symbols there, I'm going to say like that, right? So where did we put this in? We put this what? In water. Therefore, this is our correct equation for the what? For this explanation of what is actually happening above. Then we proceed to question 8. So question 8 is there. An electrochemical cell is set up under standard what conditions, right? So write one function of part X, right? So part X there, we know it's a salt bridge, right? So X is our salt bridge there, right? So it's a salt bridge, right? Then if it's a salt bridge, now the functions there is number one. So function number one, it completes the circuit. So completes the circuits. So that's our option one there. Completes the circuit. Then number two, also as an option, is say it neutralizes excess electrons. So it neutralizes excess electrons like that. So this is what we're having. Then we can also add another point. So it means here it actually provides a path for the movement of ions, right? So it also provides a path for the also movement. Allow me to use MVT, movement of what? Of ions, right? Ions, right? So we are supposed to just pick one from these: completes the circuit or neutralizes excess electrons. Then number three, it provides a path for the movement of what? Of ions, right? Then to proceed to 8.2 then. So 8.2 says which electrode of the cell is an anode, right? So we're looking for the anode there, right? And then write down copper or He, right? So in terms of this there, we are supposed to refer to our tables there to make it easy. Let's just like quickly go through the table there. So what are we given? We're given our copper and our He, right? So copper and our He. Let's look for copper there. Okay, this is my copper there, right? With a positive 0.34. And then also, what am I looking for? There is actually going to be my zinc. Is it zinc? Let me just like confirm there. Silver. So it's actually a silver there. It's silver 0.80. Okay, so this is my silver there, right? Okay, so these are the ones that are actually highlighted that we're looking for there, right? So according to this, it means this one there is actually going to be my anode, right? So this is going to be my anode. So my copper is going to be my anode, and then this one is actually going to be my what? My cathode, right? Okay, so like that. So the more positive it is, it becomes a cathode, and then the more negative it is, it's going to be what? Less positivities, it's an anode, right? So according to this here, we asked what? Write an electrode that is an anode, right? So in terms of this, our anode there, according to this already, we said is what? Is copper. Therefore, our answer there should be what? A copper. So our anode there is actually our copper. Okay, and just write it on the side. Therefore, it's Cu there. That's the answer. I write down the name or formula of the electrolyte in the copper half cell, right? So it means we're focusing on this half cell there, right? So usually whenever we're having here, it means here they are what our sulfate there, right? They are our sulfate there, right? So two negative there, this is our sulfate, right? So it means now for our copper half cell, what is actually going to happen there? It means now the electrolyte that is actually going to be used there is actually what our copper sulfate, CuSO4, like that, right? And then the silver electrode again. So here, if we were to use our nitrate, maybe NO3 negative, so NO3 negative. So it means this one is going to be our what? Our silver nitrate. So I'm going to say HeNO3, right? HeNO3, right? So we're going to have our nitrate then. Then to proceed to 8.4, it says write down the balanced net cell equation for the above cell, right? So for me to write this one down there, it means now what I'm supposed to do is to start with that equations. So I'm just like taking these equations there, this one and that one there, right? So I'm going to start with the one for copper. So I'm going to say my copper there was Cu2 plus, then plus 2 electrons to give me a reversible reaction of Cu, right? So to give me Cu, then my silver there was my He plus, then plus an electron there to give me a reversible reaction of what? Of silver, which is my He, right? So according to this, we already said this one is going to be my anode, right? My anode like that, okay? Then this one is going to be my cathode, right? So remember what we do with the anode, right? We flip it. Why do we flip it? Because now oxidation takes place at the anode, right? So oxidation, how do you define oxidation? It is the what? The loss of electrons, right? So in terms of this, it means it's gaining electron. Therefore, to show an equation that indicates the loss of electrons is going to be Cu to give me Cu2 plus, Cu2 plus, sorry, Cu2 plus, not 2U plus, Cu2 plus, Cu2 plus, plus what? 2 electrons, right? So this is what is going to happen at the anode there, right? So just to rewrite that one, anode there. So what is happening at the anode? This is what Cu, then to give me Cu2 plus, Cu2 plus, Cu2 plus, plus 2 electrons, right? Then what is actually happening at the cathode there, we're going to write it as this. So what I'm having there, I'm going to say my He plus, plus an electron to give me what? An He, right? So this is what I'm having there, right? So now for me to write the net cell, overall net cell, balance net cell overall equation for the above cell, right? So what I need here is to like balance the number of electrons, right? So as you can see here, what I'm having there in terms of the number of electrons, they are not balanced, right? So the copper is having what? 2 electrons, and then this one is only having 1 electron, right? So it means now I'm going to put everything in bracket and then multiply there. So it means now for my cathode there, I'm going to have a 2 He plus, then plus 2 electrons to give me what? 2 He there, right? 2 He. So 2 He. So this is what I'm going to have, right? So now to write the net cell equation, that now I'm going to say to put everything together, starting with the anode there. So the anode there, I'm going to say is a Cu. Then I'm going to add this one here. So after that, I'm going to say Cu plus 2He plus, then plus how many electrons? 2 electrons, right? To give me, then I'm going to go back to the anode and finish whatever is on my right there. So it's Cu2 plus, plus 2 electrons, then plus again at the bottom there. What are we having there? We're going to have 2He like that, right? So now in terms of the number of electrons now, we are actually going to not include them because they cancel out each other like that, right? So the final equation there that we're going to have there is going to be what? Cu plus 2He plus, plus 2He plus, and then to give me a Cu2 plus, Cu2 plus, plus 2He like that, right? So this is the final one there that we're going to have there. So this is where you're going to get all your marks. So write down your balance. So it's balanced like that. Can you see the number of electrons are also what? Balanced. Then after that 8.5 there says allow me to just like divide that small space there. So for 8.5, okay, then I'll use a different color. So for 8,5, it says they calculate the EMF of the cell, right? So the EMF of the cell is equivalent to E theta cell, right? So according to this, take note of this. We are going to write this as it is, right? So it says here E theta cell is equivalent to E cathode minus E anode, right? So I'm going to write that one down as it is. So I'm going to say my E theta cell there. E theta cell. So E theta cell is equivalent to E theta for the cathode, right? E theta cathode. Take note, do not write E cat. Okay, so E theta anode like that. Okay, so please write it in full. Write it in full. So therefore, my value for the anode there is actually, I mean, 0,80, and then I'm going to say minus for the this one 0,34. It was a positive, right? So just had to look at those values. We're having silver and what's okay, copper. So can you see these are the values that I'm using there? Let me just like use a black there to highlight. So these are the values that I'm using: a 0,34 for the anode and then a 0,80 for the cathode, right? So these are the values there. So if I do my math there, I'm going to get a value of 0,46 volts. Okay, so take note, your E theta cell is always going to be a positive value. So if you get a negative value, just know you made a mistake. Just erase and start all over there. Okay, so then 8.6 says the standard conditions under which this cell operates, right? So we need the standard conditions, right? So standard conditions that we actually have here is going to be temperature. Okay, so I'm going to say temperature. Okay, I need to be specific, right? So here is actually what, 25 degrees Celsius, or if you want Kelvin temperature, is equivalent to 298 what kelvins, like that, right? Then also we need the concentration, right? Concentration. So what concentration there? I'm going to say 1 mole per dm cubed. Right, that's the concentration that we need there. We need the temperature at 25 degrees or 298 kelvins, and then the concentration at 1 mole per dm cubed. So those are the conditions that we're looking for. Then to proceed to question 9 there, it says the simplified diagram below represents an electrochemical cell used for the purification of copper. So we're purifying copper. According to this, let me just label these terminals. So the longer one there, this longer line is going to be my positive, and then this shorter one is going to be my negative, right? So now, state the energy conversion that takes place in this cell, right? So the energy conversion there is from electrical energy to chemical. So electrical to chemical. So I can just say electrical to chemical, right? Okay, electrical to chemical. So that's my energy conversion, right? Then after that, define the term electrolyte. So an electrolyte is a solution that conducts electricity. Okay, so I can just say a solution that conducts electricity, electricity. Okay, how does that it do that? Through the movement of ions. Through the movement of ions. Movement of ions, like that, right? So this is our answer there. A solution that conducts electricity through the movement of ions. The 9.3 there, we are asked which electrode contains impure copper, right? Impure copper. So the one that is not pure there, write down electrode A or electrode B, right? So according to my analysis, there is going to be electrode A. Then I will explain why. So A there is the positive terminal. Remember, in terms of this, the positive terminal in terms of this is actually going to be what my anode, right? So my anode there, then I'm going to say anode, then I'll actually explain what happens at the anode. So oxidation takes place here, oxidation takes place there, oxidation here, right? So by definition, how do you define oxidation? Is the loss of what electrons, right? So loss of what, of electrons there. So that's my oxidation, right? So it means this one is going to lose these what are electrons to what, to electrode B, right there, right? So now, and also the mass of this is actually going to decrease at the end of the day. This anode is actually going to decrease in what, in mass, right? So my correct answer there is which electrode contains impure copper. So I'm going to say my answer there is electrode what, electrode A. Then we proceed to 9.4. 9.4 reads write down the half cell which takes place at electrode B, right? So we're focusing on electrode B, right? So as you can see at electrode B, what you're going to have there is our copper, right? So if we're having our copper there, right? So what happens at the cathode? So this is the anode and then the cathode, right? So I'm going to say cathode on this side, right? So this is the cathode that I'm actually going to have there. This is the cathode that I'm actually having there. This is the cathode that I'm actually having there. So at cathode there, what actually happens there is actually what a reduction, right? So I'm going to say reduction happens at the cathode, right? So reduction takes place at the cathode. Then after this now, if reduction takes place at the cathode, what also do we define? How do we define reduction? Is defined as the gain of electrons, right? So reduction is the gain of what? Of electrons, like that, right? So we're gaining our electrons then. Then after that now, it means according to this, our copper there, so there is a gain of what? Of electrons. Therefore here, write down the half reaction that takes place at the electrode. So I'm going to take my copper there, right? So I'm going to say my copper there is going to be Cu and then 2 plus, right? Plus 2 electrons, right? So can you see we are gaining these electrons, right? Then to formulate our what? Our copper. So we're gaining these electrons from this electrode to that one there, right? So these 2 electrons, these are the ones that we're having there, which is the gain of what? Of electrons, right? So a simple trick, once you see your electrons on this side here, it means we are losing electrons. But if you see them on your left, it means we are gaining, right? Then at the end of the day, number 9.5 there is A. Is electrode A an anode or the cathode, right? So already we have actually identified that one. A is the what? Is the anode, A anode. So A for anode, I'm kidding. Just but A, according to the analysis, this is the positive terminal. Your A is the what? Is the anode there, right? So after that, we are saying 9.6 there. It says the 2 electrodes are replaced with carbon rods, right? Then if they are replaced with carbon rods there, it says here 9.61. Write down what will now be observed at electrode A, right? So here at electrode A, here we usually see gas bubbles that are actually going to formulate around this one, right? So in terms of this, since we're having our chlorine there, I'm going to say this chlorine gas is actually going to what? To formulate at electrode what? A. Then to proceed to the last one there, it says 9.6.2, write down a relevant half reaction that explains the observation made in question 9.6.1 there. So now we need to write down a relevant half reaction that explains the observation that is made in question 9.6.1, right? So according to this there, I'm going to say the chlorine, since it's diatomic, that's how I'm going to say 2Cl there, right? So to give us a Cl2, which is a gas, right? Cl2 plus what? 2 electrons there. So this is how we are supposed to write the final part of the question. Okay, that's the end of this question. I hope you actually enjoyed it. Thank you.